Separation processes sometimes make use of membranes to filter out impurities in fluids. Some of these processes are microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. In this video, we'll be talking about microfiltration. You might ask, what is microfiltration? Well, microfiltration is a type of physical filtration process. During this process, contaminated fluid is passed through a special pore-sized membrane to separate microorganisms and suspended particles from processed liquid. In other words, microfiltration refers to filtration of a liquid suspension through a membrane with pores of approximately 0.1 to 10 micrometer in diameter to retain microorganisms and other suspended particles from the processed liquid while transmitting solutes that are smaller than the membrane pores. We will be using the treatment of water as a case study to describe how the process of microfiltration occurs. First, untreated water is pushed through a tube of hollow fibers. These hollow fibers will trap large pollutants like protozoa, bacteria, and suspended solids. However, more microscopic, atomic or ionic materials such as water, viruses, dissolved or natural organic matter, or small colloids could still pass through the filter. A typical microfiltration system comprises several essential components. These are a membrane module, a pump, a feed tank, and a pressure control system. The membrane module houses the filtration membranes. These membranes are crafted precisely to ensure the desired pore size and permeability for effective separation. A pump generates the necessary pressure gradients across the membrane, driving the fluid through filtration. The feed tank stores the solution or suspension to be filtered, ensuring a steady supply to the membrane module. And to ensure better performance and prevent membrane damage, a pressure control system monitors and regulates the pressure applied during filtration. The microfiltration system also makes use of the sieving mechanism. It is the primary mechanism, which is size exclusion. Particles larger than the membrane pores are physically blocked, forming a cake layer on the membrane surface. It also makes use of membrane characteristics. Membrane pore size, porosity, and surface properties significantly influence filtration performance. Some laws and equations that are used in the microfiltration process are Darcy's law, which is a fundamental principle in fluid mechanics that describes the flow of a fluid through a porous medium. In the context of microfiltration, the membrane acts as the porous medium and is represented by the equation, where J is the volumetric flux, or the flow rate per unit area. Delta B is the transmembrane pressure, which is the driving force for fluid flow. Mu is the viscosity of the fluid. R is the total resistance to flow. Next is the Herman's-Brill equation, which specifically addresses the decline in filtration flux over time due to membrane fouling. It is also represented by the equation, where J is the instantaneous flux at time t. J0 is the initial flux, or the flux at the beginning of the filtration process. K is the fouling constant, which is a parameter that characterizes the rate of flux decline, and T is the time.